Hello everyone, my name is Javo. The topic I'm going to talk today is a novel framework xMem that accurately predicts the GPU memory required for a deep learning training job. The key point is that it performs this task entirely on the CPU without requiring any GPU. As we all know, we are currently facing a critical shortage of GPU. The global demand for those resources far outpaces the limited supply. And this supply crunch is driven by multiple factors, from physical chip supply to the massive power requirement of data center. As a result, GPU have become a pressure and scarce resource. At the same time, we are also facing two additional issues in clusters, which add more pressures on already stranded global GPU resources. On one hand, we have failure from under-provisioning. This is when we don't correctly estimate and fail to give a job enough memory. The job simply crashes and all time and resources used up to that point are completely wasted. On the other hand, to avoid those crashes, we take a simple just-in-case approach and give a job far more memory than they need. This holds the memory, leave it idle and unavailable for other tasks. There are two numbers showing how bad failure and wastes are in this production environment. For failure, studies on production clusters at Microsoft and Meta show that about 9% of all failed deep learning jobs are caused by auto-memory issue. Another number from Alibaba data center showed that on average GPU memory utilization is often below 60%. This means 40% of those precious reserved memory is just wasted. This efficiency is literally money lost. So, efficient and direct solution is accurate GPU memory estimation, which can mitigate the waste and maximize our valuable resource. However, estimating GPU memory isn't as simple as it sounds. There are some major problems we need to figure out. The first problem is, what is the target? I'm going to introduce the two concepts here. The first one, tensor memory. This is active memory used by individual tensors, like parameter activation at any given time. The second one, segment memory. This is total memory pool reserved by allocator to improve response time when program requires memory. Look at this diagram on the right. The green tensor represents the active memory. The purple segment shows the actual GPU footprint reserved by allocator. So our goal is to predict the peak segment memory, not just the tensor memory. The second problem is that memory behavior is dynamic, making static analysis unreliable. We conduct a simple experiment by moving one line of code from position 0 to position 1 and keep all other configurations same. Look at the right diagram, the peak memory jumped by 500 megabytes by this tiny change. This unpredictable jump is exactly the problem we need to solve. Therefore, we think that capturing those dynamic behavior is crucial since we are not able to capture those data from static computation graph. The last point is understanding when an out-of-memory issue happens. Our tuition is that it would crash the first time it failed, but it's wrong. By diving into the source code, we found that it relies on how the allocator works internally, like a reclaim mechanism. When allocation fails, it doesn't crash. First, it runs garbage collection and retries. If that still fails, it frees all available cached memory and does the last retry. The out-of-memory issue only happens when the last retry fails. So, in order to accurately estimate the memory, we have to reproduce those mechanisms during the estimation, making a more accurate result. Facing all above problems, existing solution fall short. The first one, static graph-based analysis. This method only looks at model structure. It completely fails to capture the dynamic runtime behavior we just saw. The second one, pre-trained deep learning model. They try to learn memory pattern, but they struggle to generalize to the new model and can't predict those instantaneous memory activity. So the last one, hybrid estimation. So this approach requires a trail run on the actual GPU. This is very costly. It also increases contention for those scarce GPU resources, and it can also cause the auto memory issue during estimation. This is where our solution, xMem, comes in. We proposed a pure CPU-based estimation framework. It requires no GPU, capturing the dynamic runtime behavior, and have a good generalization. Before moving on to the solution, let's pause for a second here for understand the philosophy behind it. In deep learning framework like PyTorch, nearly every logic computation, like linear layer, has both CPU and a CUDA implementation. Well, the high-level logic in computation graph is identical. The actual memory activities on the hardware could be similar or different. This led us to our key design question. Is it possible to build a map between them? Particularly, can we run job only on the CPU and then capture the memory sequence and reply the sequence in a given allocator, like the CUDA caching allocator, to predict the memory usage for CUDA? The answer is yes, but we had to overcome three major challenges to make our solution work. The first one, how to get the accurate GPU or CUDA memory information from CPU information. The second one is how to align the CPU behavior with the CUDA. The third one, how to predict the final segment requirement from the tensor memory information. To solve this, we designed this framework with three core components, each one directly targeting one of those challenges. The first component is analyzer, which filters all the raw data and works by linking the high-level Python code to its implementation and the memory it's used. Its key job is to select the memory activities that are created during the execution of the operator. All other noise is thrown away. The second component is orchestrator. One of the key jobs is to fix the major difference in the deallocation behavior between CPU and CUDA. Let's use gradient memory in backward propagation as an example. Say has same behavior in creating for both CPU and CUDA training, but the deallocation behavior is different. On the CPU allocator, the allocated memory are freed almost immediately. But on CUDA, this memory is held in the memory until the zeroing function is called. Therefore, the orchestrator is used CUDA-specific logic delayed free on the CPU events, creating a more accurate timeline. Here is our last component, the allocator simulator. It's a high-fidelity two-layer simulator of the real GPU allocator, indicating the key feature, so the two-layer allocator, BFC algorithm, memory reclaiming mechanism, and the memory caching. Our validation proves it. The real segment scale is perfectly matched by the simulated segment across the three models here. To evaluate xMem, we conducted a large-scale simulation involving 1,306 test configurations, which included 22 models and 6 optimizers running on the 24-core CPU with 128 GB of RAM. We collected our ground truth data by running those tasks on the two GPU on identical hosts. We then compare the xMem estimation result against the three sort baseline: xMem, DNMem, Shelton, and ALMem. There are three core metrics here to evaluate the performance. The first one is median relevant error (MRE). This is our accurate matrix. The second one, probability of estimation failure (PF). This is our reliability matrix. This is likelihood of under-provisioning, which case out of memory issue, when we set the estimated GPU memory as the maximum runnable memory for the task. The third one, the memory conservation potential (MCP). This is our benefit matrix. It quantifies the average memory saving per run. One more thing, as we are using the same color schema across all diagrams, our solution xMem is always in blue color. First one, let's move on to the accurate diagram. There are two box plots. Upper diagram is for the CNN. Since the LLM solution is not designed for the CNN model, so its result not exhibited here. The lower diagram is for the transformer model. The conclusion is also very clearly for our solution. xMem is constantly accurate with very low and stable error across all models. In contrast, the other baselines show errors that are both high and very spread. Overall, xMem achieved a 91% reduction in MRE. Next diagram is a four-quadrant diagram. The bottom left optimal zone is the best. The x-axis is PF, y-axis is MRE. So rest of three zone means the first one under estimation, yellow one is case small out of memory issue failure. The overestimation zone is light blue with the more GPU resources, and the red worst zone, which means the worst for both. The result is clear. xMem is the only method in which almost all results are placed in the optimal zone. This means we prevent out-of-memory failures without wasting resources, achieving a 75% reduction in PF. Let's move on to the last benefit diagram measured by MCP. This is not diagram, it's a table. This table shows our memory conservation results. The number are in gigabytes, and the larger is better. Looking at the overall row, you will notice the baselines saved very little, whereas xMem saved 7.82 gigabytes per row. This represents a 368% improvement in memory conservation compared to the average value of other baseline. Additionally, there is a quick note. Sheridan's negative value is simple because this pre-trained model was only trained on CNN model, not for the transformer. The last page, conclusion. The first one, we introduced xMem, a CPU-only framework that accurately estimates GPU memory needs without using any GPU. The second one, our core technique is a high-fidelity translation, where we map the dynamic CPU memory into CUDA similar memory sequence. The third one, our solution reached 3% MRE and 14% PF. Ultimately, the auto-performance matrix increased significantly memory conservation by 368%. The last one, since we recognized that the CPU is also underutilized in the cluster, our solution can utilize those idle resources to address waste and failures for the GPU. For the future work, we are accurately expanding this research to include a distribution scenario. Additionally, we aim to visualize the layer-wise difference in memory usage for the same model between the estimated GPU memory and actual CUDA memory, considering both forward and backward propagation stages. Here I also have a question which is asked by my colleague. Is I think it may also interesting for you. So, did the different GPU architecture or type of the GPU potentially impact the estimated result? Well, based on all data we gather from the NVIDIA 4016 is Ada architecture and the 3016, which is Ampere architecture in this shown on this presentation. We also conducted experiments on the 800 GPU. Honestly, there wasn't a significant difference among the results, so they almost land up closely. In the end, I'm sorry for that I can't present my work in person due to the visa issue, and please feel free to contact me via email just shown here, and if you have any question. Thank you for listening. Bye.